Hello everybody, welcome. Today our lecture is gonna be about helical spring. Helical spring is used virtually everywhere, especially in the mechanical function of a machine. Nowadays it is constantly being used in an aerospace aluminum parts of an airplane, especially where the screw is used. By inserting helical spring into the screw hole to prevent the aluminum pitch from being damaged due to constant vibration when the engine of an airplane is running. Coil spring, also known as helical spring. This is a coil spring. The coil serves as a shock absorber. It is very good in absorbing shock and capable of storing energy and eventually release it. In most cases, a helical spring is made of a material that has a very high modulus of rigidity. Here's the helical spring. The spring look like when you're looking down. This is the top view of the coil. The R here is the radius, the internal radius of the coil, and D is the diameter. The Y here is the deflection of the helical spring when it's compressed, and eventually release the load going back to its original position. That's why it has plus for going up and minus when it's compressed. The helical spring can function either compression or tension. They both have the same capability of storing energy. The tension or compression, same thing. It will eventually goes back to its original position when the load is released. Helical spring, when loaded, for example here the load is on top of the spring. When the load is applied, the entire body of helical spring will experience two combination of stresses. Number one is a torsional stress, and number two is the shearing stress. The high amount of torsional stress occur at this junction here, and this intersection here, when the spring is changing direction from going up in this direction, then turn to the other direction. It is the torsional stress occurred here because when the load is applied, this part of the spring here, this part here will go down, and since this part of the spring is position of going up, that going down force is resisted that, and therefore there's a twisting of the body of the helical spring occurring here, and that twisting motion is called the torsional stress. The shearing stress is right here, the interbody of all of it in the helical spring, and the shearing stress is analyzed as when this part of the spring goes down altogether, this part of the spring here will resist that resistance of two forces going down and going up is a shearing stress. That's why the shearing stress is occurring over the entire body of the helical spring. Therefore, it has torsional and shearing stresses. Now here's the torsional and shearing stress formula. The S&S here is the torsional shearing stress of helical spring, and it is calculated as 16 times PR divided by pi d cubed. The d here, the small d, is the diameter of the helical wire itself, the helical spring itself, the diameter of that. And the second, by the way, the y here is formulated as 64 PRN. The n here is the number of coil. So depending on how many number of coils you have, the y here is the deflection for one coil, and if you have several coils, you multiply that by number of coil, you get the total deflection of the spring. So y is equal to 64 PRN divided by the modulus of rigidity times diameter of the spring coil itself to the power of 4. To the power of 4. And the second formula, all the these three formulas, all the very first part of the formula are the same. The only difference is the second part. Here in the number 2 formula has an M. The M here is 2R over D, and it's equal to the diameter of the internal diameter of the coil divided by d small d, diameter of the wire itself. So substitute the M here, you get this formula, and plus 0.615 over M as well. The third formula is almost the same as the second formula that has an M. That says an M here. It's 1 plus, this is 0.5 now instead of D. It's a 0.5 over M instead of 4R. So we have 3 different formulas for the torsional shearing stress of helical spring. Now let's get to the problem solving. Here in this illustration we have 2 springs suspended from the top and welded in the bottom at a horizontal bar with a length of 12 feet. The bar has a load of 500 pounds. The bar is pinned at point A, restricting it from moving down when load is applied. The only movement of the horizontal bar when loaded, which is 500 pounds, is to deflect down. The maximum deflection is right here and 0 over there. So therefore it is. And then to analyze that loading analysis, you have to draw a line from A all the way to the applied load, forming now a triangle. As you can see in the triangle here, the P1, P2 and the applied load, they are proportional. P1 is always smaller than P2, and P2 is always smaller than the applied load. They are in proportion. P1 has no choice to have smaller load than P2, and P2 have no choice to have smaller load than the applied load. So to analyze that load, we have to draw the free body diagram of the load, which is right here. 500 is here, P2 here, P1 here, and in equidistance to each other at 4 feet each. By similar triangle, we can solve for P1 and P2. This one here. Alright. We take summation of moment at A equals to 0, and P1 has a lever arm of 4, so therefore P1 divided by 4 is equal to 500 over 12. That's equation 1. And P2 has a lever arm from A of 8 feet, so therefore P2 is divided by 8 is equal to 500 over 12 in equation 3. And by saying that P1 is smaller than P2 and P2 is smaller than the applied load, we can write this formula by writing P1 plus P2 is equal to 500 pounds. This is an equation 1. This is the general equation of the load analysis. Okay, so whatever we get here, we have to substitute that to make sure that our answers are correct. So P2 now has P2 over 8 equal 500 divided by 12 is equation 3. Now we are using equation 2 and 3 solve for P1 and P2. By cross multiplying equation 2, number 4 goes there, so therefore P1 over 500 divided by 12 times 4 over 1 is equal to 166.67. And then by cross multiplying equation 3, we get P2, and number 8 goes there, so P2 now is equal to 500 over 12 times 8 over 1 equals to 333.33 pounds. Any whole number is understood to have a denominator of 1, so I just put it here to make it proportional and looks good. Alright, so we have 166.67 P1 and 333.33 pounds the P2. Now, to make sure that our answers, both our answers are correct, we have to substitute these values in the general equation number 1. This is P1 plus P2 should be equal to 500. Now we can solve that. By substituting P1 is 166.67 plus 333.33 equals to 500 pounds. 500 now is equal to 500 pounds. Okay, therefore our answer now is correct. Okay, now solve for this torsional shearing stress of the spring 1 and spring 2. Solve for stresses for each spring. Let's start with the bigger load, the P2. Using this formula here that we discussed earlier, S sub S, SS P2, that is the spring number 2, substitute the value there, which is 333.33 times 2.5, this is the radius, divided by pi times the diameter of the coil itself to the power of 3, and multiply by 1 plus the diameter of the coil wire times 4 times the radius 2.5 inches, and SSP2, the wire feet of the stress for wire P2 is 278,340.73 pounds per square inch. And now let's go to P1. So that's the load of P2 there is 278,000 psi, more than 278,000 psi. Now to solve for this torsional shearing stress of P1, substitute that value there, the P 166, 16 times 166.67 times 2.5 divided by pi 1/4 to the power of 3 times 1 plus the diameter of the coil itself, the wire itself, multiplied by 4 times the radius, gives you the torsional shearing stress for P1, the spring one, is equal to 139.74 .54 psi. So you see that because of the proportion of load, the P1 and P2, P1 can only be stressed so much compared to P2 because of the loading arrangement here. There's a restriction at A here, so that's why now the P2 is always larger than P1. The spring one carries larger stress than the spring number. Now the spring 2 carries larger stresses than spring number 1. Now here's the looks for as I've said earlier, used in the helical spring used in the aerospace parts. Parts of an airplane is usually made of aluminum. When the engine is running, there is a large amount of vibration inside the engine, and more likely aluminum can be damaged easily with a screw. When screw is installed, to prevent that, the invented now for aerospace parts, especially with the screw, they inserted this helical spring like a screw, designed like a screw, inserted it in the screw hole so that the helical spring will protect the screw parts of the pitch of the aluminum parts. See here, the helical spring is sandwiched between the screw and the aerospace parts itself. That's how they do it now. So that's the use of the helical spring, and so that now the screw is in contact with the helical spring, not to the parts itself. As I said before, the helical spring absorbs shocks and vibrations very good in shock and vibration absorption. So this is the thickness of the aluminum plate. This is the aluminum plate right here, the screw is right here, and the helical spring is in the middle. The materials: aluminum plate, helical spring, and even stainless steel. Any kind of screw you can put it there because it's protected. Alright, so that's the helical spring and the importance and the use. It's a beautiful mechanical device actually. And that's the end of the video, and I hope you like the video, and don't forget to subscribe. Your subscription really makes a lot of difference to make this my channel grow. There's more video to come. I need some time to do it. Alright, thanks for watching, and bye.